Here's a short investigation where we're going to investigate total internal reflection. Okay, now it's related to refraction, but it's a little bit different. There's a little bit of reflection as well. Okay, right, now it's going to happen between the boundary between two transparent media. In this case we've got perspex and air. Okay, right, we used rectangular perspex blocks before, but this time we're going to use semicircular. The reason is, I'll explain in a minute, but what we want is the semicircular transparent block on the paper. We're going to draw around that neatly. Now I'm going to take that away because we want a normal. We want to draw a normal. Okay. Now the normal has to be perpendicular, but we want the centre point. So that's 9 centimetres, 4.5. That's going to be our midpoint. That's going to be our targets to aim for with our ray box. Right. You can use a set square here to draw a nice perpendicular normal. So there's going to be our normal. So this is going to be our target, but we're going to come in from the top. Now the reason is because if we use a semicircular glass block or semicircular perspex block, as long as we hit the target here, we'll always be hitting the curved side at 90 degrees. Even if we come in at a big angle, a small angle like that, okay, the incident ray is hitting this boundary at 90 degrees. If we come in at a really small angle, we're hitting at 90 degrees. Even if we come in at a really big angle, we're hitting at 90 degrees. But we're not interested in what's going on at this boundary. That's why it's circular. We're interested in what's happening at this boundary here. Okay, so let's just position that correctly. Looks good. Now we're going to start with a small angle of incidence inside the block. Okay, right, what are we seeing here? So the ray's coming in here, yeah, it's hitting here at 90 degrees, but there's a small angle of incidence between the ray in the block and the normal. What are we seeing here? Well, we're seeing refraction, aren't we? But we're seeing it refract away from the normal. Okay? Now, if we increase the angle of incidence, remember the angle of incidence is the one inside the block. It's between the block, the ray inside and the normal inside. But if we increase the angle of incidence, the angle of refraction here also starts to increase. Also starts to increase. Now we should be able to start to see a reflected ray here. Now there's a faint reflected ray. Okay, I'll turn the lights off in a minute, and there's the refracted ray. But as you can see, that refracted ray is moving more and more and more parallel with the edge of the glass of the perspex block. Right, much better if I turn the lights out. So let's go back to a small angle of incidence. So as we can see, the reflected ray is quite obvious there. The refracted ray is quite obvious, and this is the incoming incident ray. So let's go back to a smaller angle of incidence. Okay. Now as you can see, we've got the refracted ray here. but we've still got a very, very faint reflected ray here. Now let's increase that angle of incidence. All the time, making sure we hit the target here. Right, if we increase the angle of incidence, that refracted ray is moving towards the edge of the block. This reflected ray is becoming more and more bright. Okay, more and more bright. Now if we come in at a big angle of incidence inside, make sure I hit the target. If I come in at a much bigger angle of incidence, we see no refracted ray at all. The only ray we see is the ray coming in and the ray being reflected out. Now that is called total internal reflection. All of the light at the straight boundary, all of the light at the straight edge has been reflected from this edge back again. So this edge here is acting like a mirror. Okay? Now, we're going to measure something. We're going to measure something called the critical angle. So total internal reflection happens, there's two criteria. It happens when this angle of incidence here is greater than the critical angle. Okay, the second criterion is for total internal reflection to take place, we have to be going from a more dense to a less dense medium, like we are here. We're going from perspex to air. Right, anyway, let's measure that critical angle. To measure the critical angle, we need to start with our refracted ray and then gradually increase the angle of incidence until that refracted ray is pretty much parallel with the straight edge. Can you see? Just about losing it there. Any bigger, we see the refracted ray. Okay. Any smaller, and it just disappears. Okay. Right, that's now coming in at the critical angle. So the refracted ray is realistically just going along the edge there, but it's just disappeared. Right, we need to trace these two rays here. So we're now coming in at the critical angle. And we turn the lights back on. And we turn the ray box off. I'm going to remove the perspex block. Now, let's with our 30 centimetre ruler. How cool is that? Draw. So there's our incident ray. Again, it's hitting this boundary at 90 degrees. As long as we hit this target here, this will always be 90. So there's no refraction here. That's why we wanted it. Okay. Now what we had there, that was on the critical angle. So we've got the refracted ray going at 90 degrees there, and we are seeing pretty much all of the rest of it being reflected. Okay, so we've got incoming, reflection, and the pretty much imaginary refracted ray along the edge of the block there. So this angle here is the critical angle. Now let's measure it. Okay. Looking like 42 degrees, which is what I expected. 42 degrees is the critical angle for perspex. One last thing. What do you think that angle is there? Okay, so if that is 42 degrees, which is the critical angle for perspex, okay, no prizes for guessing that that is 42 degrees there, because this is reflection. We're seeing reflection here, and the law of reflection is true as it will be for mirrors. Okay, so there you have it, total internal reflection.